Hey, welcome back to the EECS 370 videos. Today we are going to be going through the winter 2023 midterm. So I have the solution in front of me and I'm going to work through the entire exam. Hopefully this should provide some ideas on how we grade it. Maybe you can find where you miss a question and you can kind of get the right reasoning to get to the right answer. But I hope that this video is very helpful to you. So we'll go ahead and start off just with the first question. We start off with multiple choice in this exam. We had 8 questions worth 2 points each. So question A says Dennard scaling roughly states that, 5 choices, as transistors get smaller, their power per area stays constant. As transistors get smaller, their power density goes down. About every 2 years, the number of transistors on a chip doubles. As transistors get smaller, their power density doubles about every 2 years, or that processors tend to get unusably hot due to power per area not staying constant. And the correct answer for this one is A. And here's why. It's because if we look at B, it says as transistors get smaller, their power density goes down. That is not true, or else we would see every year devices getting more and more efficient. It's just not what Dennard scaling says. Instead, we see the effect from Moore's law, which is actually what part C is. Moore's law states that about every 2 years, the number of transistors on a chip doubles. When we combine that with Dennard scaling, which says that the power per area stays constant, then we get more compute power in a chip about every 2 years while using about the same amount of energy. So those trends are kind of going away, unfortunately, but that is what Dennard scaling says. Part D is not true. As transistors get smaller, the power density doubles. That would be very bad. We'd be sucking in a lot of energy, and there would be not much of a reason to get smaller transistors. And then that would be the same as saying part E, where if we had transistors that had power density doubling, that means that they would probably get unusably hot, which would be very bad for us. So A is the correct answer. Let's move on to B. We're given a logic gate diagram, and we're supposed to come up with what it represents. All right, so let's break this down into multiple parts, starting with this part here that I've boxed. That's a NAND gate with A being both of the inputs. And so that's just going to function as a NOT gate. And the same for the bottom part. So far we have a NOT A over there, and then a NOT B over here. Then we have another NAND gate combining those two results. And then finally we have another NOT gate at the end, or rather a NAND gate being used as a NOT because the same input is going to both of the NAND gates inputs. So we essentially get a double negation, crosses out, and we get in the end NOT A and NOT B, which by De Morgan's law is equivalent to NOT A or B. So in the end, this is a NOR gate, and B is the correct answer. Question C, which 2 of the following are the primary reasons we prefer not to use latches in our computer designs for things such as the mem write-back pipeline registers? So if you remember, we'll see this in a later problem, but a latch is a logical device where anytime the gate is high, the output of the latch is going to match the input of the latch exactly, plus or minus some amount of delay. Versus a flip-flop, that is where the value is copied at the instant that the clock goes from low to high. The clock and the gate kind of being synonymous here. Just to recap, when the latch has a high signal, it's going to copy the input to the output the entire duration that signal is high. When we have a flip-flop, that value is going to be copied just at one instant. And all other times for both latches and flip-flops, it's just going to hold the last value that it got. So let's look at these possible answers. It's like true or false. So number one, if the gate signal is set high for too short of a time, there may not be enough time for feedback to stabilize in the latch. Two, if the gate signal is set high for too long of a time, signals from the EX stage may have time to impact our output before the gate is set low. Three, if the gate signal is set low for too long of a time, the pipeline register will lose its data. And four, if the data signal is changing as the gate goes high, the latch's output will be unstable. So let's look at the incorrect answers first. Our first incorrect answer is 3. If the gate signal is set low for too long a time, the pipeline register will lose its data. That's not really an issue for registers, especially in the pipeline register, because the pipeline register is going to be updated every single clock cycle. And if you have a register that can lose its value in a time period shorter than a clock cycle, then your system probably just doesn't work at all. There are different types of memory, volatile memory that can lose data, and that's really outside the scope of 370. But registers that are updated every single clock cycle should not be losing their data, or else nothing would work ever. If we remember just kind of the basic implementations of our latches and flip-flops, they're just gates. So if our gates are somehow losing values as they're propagating through different gates, then we need to improve the reliability of our system in general. So 3 is incorrect. 4 is also incorrect. It's asking about the moment that the gate or the clock goes from low to high. So we said a flip-flop changes at that instant. But if we're thinking about a latch, that's the instant where it starts copying from output to input. So if the data signal is changing as the gate goes from low to high, well, then that change will be represented. You'll see it in the waveform for the output of the latch. For the flip-flop, you don't know. You don't know the precise instant that the flip-flop is going to capture it if the input is changing at the instant we would expect the flip-flop to capture the value. So we don't know if it'll capture that value right before or right after. And if you want to learn more about that, you can look at X270 that has to do with a setup time and hold time. Not particularly relevant to this question since this question is asking about gates, or sorry, latches and not flip-flops, but that is something that we would have to think about with the flip-flop. So 3 and 4 are wrong, which leaves 1 and 2. Looking at 1, if the gate signal is set high for too short of a time, may not be enough time for feedback to stabilize in the latch. That's absolutely true, because since our latches are made of gates, there is going to be some sort of propagation delay. And you might remember our basic latch looks something like this. And if it's going through these gates and there's some sort of gate signal that's affecting the set and reset parts, then we might have some sort of inconsistency between this wire, let's call it Q, and this wire, not Q, and that could cause it to stabilize to an incorrect value in the end. So that would be bad. And then 2, if the gate signal is set high for too long of a time, signals from the EX stage may have time to impact our output before our gate is set low. That's also true. Let's see. So I can draw it out. If we have our EX stage, which is made up of a bunch of components and wires and gates and things, and if this is our IDEX pipeline register, we're looking at a different one. We're looking at the, we're looking at the mem write back pipeline register on the right. So there's mem write back. Here's the EX mem. If we're using a latch, then these signals from the EX stage might reach the EX mem pipeline register quicker than the signals from the mem stage, and then they would just flow straight through because our latches allow signals to flow through. They just copy values. They don't really stop anything when the gate is high. So that would mean that it could potentially change what address we load from memory. It could change some sort of write value. We really don't know what it could do. So we do not want to be using latches for our pipeline registers. All right. Moving on to question D, we're asked to write -6 as a 5-bit 2's complement binary number. So if we're thinking about 5-bit 2's complement, that means that we have 4 numbers, 4 bits with positive place values. So 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3. And then bit number 4 is going to be -2 to the 4, which is -16. So in order to write a negative number, we definitely need to make sure that our negative place value has a 1. From there, if we start with -16 and want to get up to -6, we have to add 10. And 10 in 4-bit binary, that is 2 to the 3rd, which is 8, plus 2 to the 1, which is 2. And then we can fill in the others with zeros, and our final answer is 11010. So let's see, 11010. Question E. What is the largest, meaning closest to positive infinity number that can be represented in a 6-bit 2's complement representation? Provide your answer in decimal. Well, same deal as question D. Our leftmost bit is going to have a negative place value of -2 to the 5, and all the others will have the other place values of 2 to the 0 through 2 to the 4. And so we will want to keep the -1 at a 0 because we want a positive number. And then all these others, in order to maximize our output, we're just going to set them to 1 and then add that up. So let's see, 2 to the 4, which is 16, plus 2 to the 3rd, which is 8, plus 2 squared, which is 4, plus 2, plus 1. That gets us to 31. 31 is our answer for question E. All right, and just to double check, here's the official solution. Moving on to question F, which of the following is true about the data hazards and control hazards in a pipeline processor? A, data hazards only occur when instructions depend on the results of previous instructions, while control hazards only occur when instructions change the data in the pipeline. B, data hazards occur when instructions depend on register values written by previous instructions, while control hazards occur when instructions change the flow of execution. Data hazards, for C, data hazards occur when the pipeline runs out of data, while control hazards occur when the pipeline runs out of control signals. Or D, data hazards occur when multiple instructions access the same control signals, while control hazards occur when instructions change the flow of data. And our correct answer, I guess, is a two-part. We have to define our data hazards and our control hazards. So we saw data hazards in our pipeline whenever we had dependencies between instructions of registers. So like, for example, if I have an LW, let's say 0, 3, 1, and I have an add 2, 2, 3, there would be no dependency since the add is reading register 2 and the LW is writing register 3. But if we were to change this register here to a 3, then we have a data hazard because there's a dependency there. There is a read after write or raw dependency. So raw is read after write. Then we saw control hazards for any branch that we had mispredicted, or really any branch in general will constitute some sort of control hazard since we don't know what PC we're supposed to execute next until we have completed the branch. And so control hazards go when we have to fetch something besides PC plus 1, pretty much. So it changes the flow of instructions. So that means that our correct answer for this question is B. It is B. So I think part A, the data hazards part of part A is correct. Data hazards occur when instructions depend on the results of previous instructions. But its description of control hazards is not correct. Control hazards has nothing to do with data. That's also why part D is wrong. And C is just kind of a non sequitur. Data hazards occur when the pipeline runs out of data. Pipeline doesn't really run out of data. There's always registers in memory that you can pull from. And control hazards don't really have much to do with control signals. when we think about our different selector bits and things that we put into the data path. That's not really a control hazard. That's just control. All right. Moving on to question G. When executing a large program that has no hazards, where every stage takes one cycle, LCK pipeline taught in class would expect to achieve a CPI of about 1, 3.5, 4, 5, or it depends on the instruction mix. And the correct answer for this one is A, which is 1. And remember, this is the whole idea behind the pipeline. We had our single cycle and our multi-cycle. The really attractive thing about the single cycle is it had a CPI of 1. And the really attractive thing about the multi-cycle is that it had a really low clock period. So we're going to combine both of those things in order to make our pipeline. And our CPI will only really get above 1 whenever we have to insert some sort of stalls or squashes. If we are completing an instruction every single cycle, except for the 4 startup stages, then we'll get a CPI of about 1. So that's why A is correct. And I guess we didn't really ask this on this question, but you might remember that your pipeline CPI is equivalent to this. So we'll have our number of instructions plus the number of startup stages. So those are in our pipeline the number 4, because you take the number of total stages in the pipeline minus 1. Then you will have your stalls, and then you have your squashes. And when I say squashes, I'm counting every single instruction that's being squashed. So I call these the 3 S's, and these are unique in that every single time you have one of the 3 S's, you have a no-op that is written back that doesn't appear in the assembly code. So it's a no-op written back that is not in the code. And then you take all that and divide it by your number of instructions. So of course we can see that if our 3 S's are all about 0, then it's just instructions divided by instructions, which is 1. Question H. What is the purpose of having some registers be caller save and other registers be callee save, as opposed to doing one or the other when making subroutine calls? A, to ensure that the caller save registers are not overwritten by the callee. B, to ensure that the callee save registers are not overwritten by the caller. C, to prevent data corruption in the pipeline. Or D, to reduce the number of registers stored to memory. Looking at A and B, these are incorrect because the question says, it asks you why would we mix instead of just having like one policy. Well, if we have just one policy, then there won't be a situation where the caller would overwrite the callee or the callee would overwrite the caller. This is one policy. And having these saves in general, the whole point is to make sure that functions don't overwrite values that other functions need. So we have to save them somehow. That's the whole point of caller or callee, and they both solve that issue. C, to prevent data corruption in the pipeline. That's a non sequitur, since caller and callee really has to do with the assembly code. The actual implementation of the microarchitecture is completely separate from how we use the code. As long as we're using the same ISA, it's the programmer's job to conform to the ISA, and it's the architect's job to also conform to the ISA on the hardware side. So those are completely separate things. So that leaves D as the correct answer, to reduce the number of registers stored to memory. And we saw that depending on if you use caller or callee save, one might be more efficient than the other in certain scenarios. So for example, when we have the main function will not need to do any callee saves because there's no caller of main, and so there's nothing there for main to save. So if it puts everything in callee registers, well, if main calls something, then those will be saved, but main itself doesn't have to do any saves. So we want to keep main's variables in callee save registers. Going on the other end, if we think about our leaf functions, A leaf function, by definition, isn't going to call any other functions. So it will never have to do a caller save. So if it puts all of its variables in caller save registers, then it never has to save them. And we reduce the number of loads and stores. We reduce our program execution time and program length and all those good things. So D is the correct answer. All right, let us now move on to question 2. Speaking of caller callee, we're going to look at some ARM code, and we're going to analyze what this ARM code is doing with caller and callee registers. All right, so it says the code below uses 2 new to us ARM instructions, push and pop. By the way, this is, I believe, from ARM v7. In this class, we've used ARM v8, of which leg is a subset. When we had ARM v7, there was a subset called thumb, just for fun. I don't believe push and pop are in ARM v8 anymore, so we have to use more complicated things in order to do that. They might be pseudo instructions, which just means that they're translated to other instructions. If you're ever interested in that, you can go look at Godbolt, which is this website where you put in some C code and it'll spit out the assembly and you can see all the different versions. If you select ARM, GCC, Linux, any version, this will put out 32-bit ARM v7 code. And then if you want to see something closer to leg like we've been using in the class, you should use the ARM 64 GCC, because 64 means that we're most likely going to be using ARM v8. So that gets you ARM v8, which is 64-bit. All right, so let's look at the code now. It says the push instruction stores the register value listed on the stack. The pop instruction loads the data from the stack and places it in the listed register. Both modify the stack pointer as appropriate to add to the stack when you're doing a push, or remove from the stack when you're doing a pop. Note that LR is the link register, or X30, which is where the return address is put by a BL instruction. And in ARM v7 code, they'll sometimes pop what was taken from the link register and they'll place it directly into the PC, which is more complicated, but they do that. Okay, so the code. So we have a few labels here, which I think is helpful to tell us kind of what the code's doing. We have main, which is a function. We have loop, which, spoiler alert, means that we're probably doing a loop. We have Tom and Bob, and then end. So let's look at the code. So we have 4 move Z instructions. We're placing different values into registers. Then in the loop, we're comparing register 4 with 5. And if it's equal to 5, we're done. We're going to branch to end. So if register 4 is starting with 1, and then kind of skipping down here, next time we see register 4 really being modified is here. If we add 1 to register 4 every iteration, then it'll start off as 1, then it'll be 2, then 3, then 4. But once it gets to 5, we will not do another iteration of the loop. So this compare combined with the increment and the initial value of register 4 tells us that we're doing 4 iterations of whatever is about to follow. All right. So going past the branch, we see a push of register 4 to the stack, then a branch link to Bob, which means that we're doing a function call. And then after Bob executes, we come back, we pop register 4 from the stack, push again, and then we make another function call to Tom, pop register 4, push it again, make another function call to Tom, pop register 4 again, and then we do something with maybe a return value of some sort, doesn't really matter, and then we go back and do another iteration. So I'm going to point out the 3 function calls that we had here. So we made, let's see, 1 call to Bob per iteration and 2 calls to Tom per iteration. And we noticed that around those function calls, we had a push and a pop. And that tells us that register 4 is a caller saved register because main is saving its value of register 4 and it's wrapping that around the function call. So we can go ahead and figure out how many loads and stores we're doing for register 4 from that information. So if we have 4 iterations and 3 function calls per iteration, so for each of these, we are making a save for register 4. So if we get 3 calls, 3 saves times 4 iterations, that gets us 12 load store pairs for register 4. All right, so now we've been through main. Let's look at our other functions. So we have Tom and Bob. So looking at Tom, we see that the first instructions in Tom push both register 1 and register 2. So this is a save of some sort. And then let's see, it does something with register 1, it modifies register 4, it modifies register 2, but then it restores the values of register 2 and register 1. So notice that since Tom didn't modify register 1 and register 2 before Tom pushed register 1 and register 2, that must mean that it's saving the caller's values. So then Tom is the callee, so this is a callee save of registers 1 and 2. Now, I'm not going to answer how many loads or stores we have yet until we look at Bob. You'll see why. Bob does something similar. It's that Bob pushes registers 2 and 3 instead of registers 1 and 2. Modifies register 2, modifies register 3, and then it restores them before returning. That's what the branch link is. That is a return. It's kind of like if we're thinking about our combination code in LC2K, that's like making a jailer to whatever register you had previously used to say PC plus 1. So the caller's register B should be the callee's register A when you're returning. That's the kind of same thing. Okay, so we see registers 2 and 3 saved. That means they're both going to be callee. Missed an E. And now we can figure out how many saves we have total. So notice that each time we call Tom, we are saving register 1 once and register 2 once. Then every time we call Bob, we're saving register 3 once and register 2 once. So that means that register 2 is being saved every function call because the only 2 function calls made are Bob and Tom. And so register 2 is going to be saved just as often as register 4, 3 times per iteration of main, 4 iterations total. So register 2 will be saved a total of 12 times. 12 loads, 12 stores. Register 3 is only saved for Bob. Bob is only called once per iteration. So 1 save per iteration, 4 iterations total gets us 4 total saves of register 1. And then, or sorry, not register 1, register 2, or sorry, 3. Let's see, 4. There we are. And that's for this one. And then finally, register 1. Let's see. So register 1 was saved only by Tom. Tom is being called twice per iteration. 4 iterations total. That gets us a total of 8 load store pairs across the entire execution of the program. So that is our answer. By the way, for grading, each of these boxes were just 1 point. So there's not a lot of partial credit. Maybe if the question was worth more, you could get partial credit for having these ratios correct and maybe the number of iterations wrong. I don't know. It kind of just depends. But for this, there's just 1 point, right or wrong. All right. Let's move on to problem 3 now. This is our pipelining question. This is a relatively basic pipelining question. We'll see much more complicated pipelining questions on the finals, but let's go ahead and look at this one. So we're told to consider the following LC2K program There's an add, a load, an add, and a NOR. And we're asked how many stall cycles does the above code incur on the 5-stage pipeline discussed in class if we're using first detect and stall and then detect and forward. So first we need to identify all of our dependencies. So let's look first between this add and this load. So the add is modifying register 3, and the load is reading register 1. The load is not reading register 3 because the load will write to register 3. So there is no dependency between the add and the load here. Let's then consider the load and then second add. So the load is modifying register 3, and the add is reading register 3. And it is reading register 3 twice, but in our pipeline, those reads would both be done at the same time. So we don't need double stalls for this dependency. We're just going to use a single set of stalls, depending on if we're using detect and stall and detect and forward. But that is a dependency. And then finally, we have between our second add and our NOR dependency, because the second add writes register 3 and our NOR reads register 3. So we have two dependencies total, one from an LW to an add and another from an add to a NOR. So if we're using detect and stall, then in detect and stall, we're going to always line up the write back stage of the source instruction with the decode stage of the dependent instruction. That's because in our write back stage, we're writing to the register, and the decode stage, we're reading the register. And as long as you have internal forwarding, which we do assume in this class, then those two things will happen at the same time. If we don't have internal forwarding, like on the project 3 pipeline, then we would have to wait until the source has left the write back stage in order to allow the dependent to be in the decode stage. But since we said it's the 5-stage pipeline discussed in class, we just have to line up the decode and the write back stages. So that means for these two stages, the execute and mem stages, between decode and write back, we need to insert some stalls. So that's going to be 2. So this is true no matter if we're doing an LW to an add or an add to a NOR or any other type of dependency. We're going to insert 2 stalls per dependency. We saw 2 dependencies, so we will have 4 stalls total. Now for detect and forward, we only worry about inserting stalls whenever we have an LW followed by a dependent instruction immediately. And here's why. Whenever we have detect and forward, we have our decode, our execute, our memory, we have our write back stages. We really only need the value of the source instruction at the beginning of the execute stage so that it can pass through the ALU. And so if an instruction has just passed from the execute stage, well, we can grab it from there. If an instruction has just passed from the mem stage, well, we can grab it from there too. If we're talking about project 3, not really the lecture or the pipeline in class, we can also grab it if it's just left the write back stage. Now, if we grab it from this spot right after the execute stage, we can do that for add and NOR instructions. We can do that for add and NOR instructions because the value that an add or a NOR will eventually write back is available immediately after that add or NOR passes through the execute stage. So you have that value, so you can use it right there and just pass it back to the next instruction. So we can take the add or NOR's value when it's in the mem stage, and it's just past the execute stage. And so if our dependent instruction is in the execute stage, say we have our add here and our dependent here, well, we don't need to insert anything between them because there's no stages between them. So now this add NOR dependency here will have 0 in detect and forward. If we're doing detect and forward with an LW though, an LW will not have its value until after the mem stage. This is because LWs have to actually get their value from memory. Sure, you'll have an address as you exit the execute stage, but you won't have the actual value that it'll eventually write back to a register. So you have to wait until the LW is out of the mem stage, then you can grab it from this point right here. So if our dependent instruction is in the execute stage, and we have to wait until the LW is in write back, in order to space them out, we must insert a no op to go between them. And so we'll have one stall for every LW followed immediately by a dependent instruction. If we have some other instruction in between the dependent and the LW, maybe it's like an SW or something, we don't need to worry about that because we can still just forward these values. LWs and write back, dependents and execute, so we're good. So that means that total, we will have one stall when using detect and forward. Let's move on to part B. Say you have an ISA where all instructions are 32 bits, which has 32 general purpose registers, and all immediate values are 12 bits. So immediately pause. Whenever I see 32 general purpose registers, I think, okay, how many bits do I need to represent those 32 registers? Well, if we take the log base 2 of 32, we get 5. So we only need 5 bits in order to represent 32 distinct values. If we had something that wasn't a power 2, we could just take the ceiling, by the way. So if we had like 40 registers, it would be 6 bits. That means that every register can be encoded in 5 bits. The same is true for LC2K. That's why our registers are 3 bits wide, or the indexes for the registers are 3 bits wide, because we have 8 registers total. The log base 2 of 8 is 3. So it says if your instruction set consisted of nothing other than instructions that use 2 general purpose registers and 1 immediate as arguments, at most, how many opcodes could your ISA support? So it says our instructions are 32 bits total, 32 bits. And it says we need to represent 2 general purpose registers at least. So that means we'll have a section of 5 bits for our first register. Let's call it register A. Then another section of 5 bits for our other register. Let's call it B. And then 1 immediate, which is 12 bits. So 12 bits for our immediate. Our immediate could be like an offset. Whatever is left, we can use for opcodes. So let's see, 32 minus 5 minus 5 minus 12 gets us 10 bits left. And so we can use all these 10 bits for our opcode. So doing the reverse of what we did with our registers, if we have 10 bits, then we take 2 to the number of that bits, which is 10, and that tells us how many opcodes we can support. 2 to the power 10 is 1024, and so that means our answer would be 1024. We may or may not accept just placing 2 to the power of 10 in the box. If it asks for our answer in decimal, we would definitely have to say 1024. But I would recommend in general memorizing your powers of 2 up to 12 for this class, since that will come in very, very handy. All right, so that is all of question 3. By the way, I do want to go over the rubric for 3B there, just so that we can see how we would grade that, because it's a lot of math. So if we had the correct number of register bits, we got a point. If we had the correct number of remaining bits, we got 10 points. So first step, take the log. Second step, do the subtraction. And then taking the exponent would be another point. So the correct final answer was the only thing that could get all 5 points. All right, moving on. Question 4. It's titled a short float. Consider an 8-bit floating point format based on the IEEE standard, where the most significant bit is used for the sign. The next 3 bits are used for the exponent, and the last 4 bits are used for the mantissa. So that's exactly what they're showing in this little table here. What bits are used for which part. It says the scheme uses bias 3 to represent the exponent rather than biased 127 used for a 32-bit IEEE floating point number. It has an implicit 1, just like the IEEE format. So what does that mean? If we have a number and we have the exponent that we want to use, let's say it's, I don't know, 12. In IEEE floating point, we just added 127, and in this case, we get like 139, and then we would convert that to binary in order to get what our exponent bit should be. So this time we'll just add 3 instead. And so notice that if our exponent is 3 bits, then we have a particular range. So we can represent 0, 0, 0. And so that would, in order to see what actual exponent that would represent, we can subtract 3. And so the lowest exponent we can represent is -3. And then if we set our exponent bits to all ones, that is 7. And if we subtract 3, we get 4. So the highest exponent we can represent is going to be 4. And then it says it has an implicit 1, just like the IEEE format. So the implicit 1, if we remember from floating point, whenever we take this number in binary, this decimal number, we leave out this 1. And we just put these bits into the mantissa. That's because we can always shift our number if it's in binary. So if we have like 0.0111, then we can just move the decimal place so that we can guarantee that a 1 comes right before the decimal. A 1 and only 1, 1. So we have like a bunch of 1s over here, and we can shift the decimal point that way. So that's why we do that. And it says this scheme is called VSF, or very short float. All right, so first, write the binary encoding of 1.5 as a very short float number. So a 1.5 is equivalent to 3 halves. And if we write 3 in binary, we will get 1, 1. So 0B, 1, 1. One color, and then we can multiply that by 2 to the -1, since 1/2 is 2 to the -1. And then if you wanted to, instead of doing like the fractional form, if you wanted to write this in your like scientific notation, it would be something like, you know, let's see. Like 1, 1 times 2 to the -1. Now here's the thing, we need to make sure that we have only one bit, 1, 1 to the left of our decimal point. So we need to add in this decimal point here, put it in base 2. And by doing that, that means that we have to multiply by another power of 2. So we will actually get 1.1 times 2 to the power of 0. And just to fill out the rest of our mantissa, we're going to add some zeros to the end of that. And so we want to make sure everything after the decimal point is 4 bits. So we will pad it with some zeros here. So that means that 1, 0, 0, 0 is going to be our mantissa. 0 is going to be our exponent, and our sign bit should be 0, since that represents positive, and 1 would represent a negative. So our sign bit is a 0. That's what we'll write first. Then our exponent, it's 0. We need to add 3. So 0 plus 3 is 3. Putting that in binary, we get 1, 1. So the next 3 bits will be 0, 1, 1. And then our mantissa is 1, 0, 0, 0. 1, 0, 0, 0. And so that kind of looks like a funky number. We have all the ones next to each other, but that is correct. Part B, what is the largest, meaning closest to positive infinity number that can be exactly represented as a very short float? This calls back to the question in problem 1, the short answer question, where we had to find the largest number that we could represent in a 6-bit 2's complement. Now, this is going to be the same. We're going to make it positive, so our sign bit will be a 0, and then our exponent needs to be as large as possible. So this exponent up here, which is the largest that we looked at earlier, it's going to be 111, but that will represent 2 to the 4. So we'll have 2 to the 4. And then if our mantissa is all 1s, when we add our implicit one, that looks like this. So 1.1111 in base 2. If we multiply that by 2 to the 4, it's like moving over our decimal point 4 places. And so this gets us 11111 in binary. And that comes out to 31. Because that's, let's see, 2 to the 4, 16 plus 8 plus 4 plus 2 plus 1, that is 31. So the largest number we can represent in VSF is going to be 31. Part C, what is the gap between 2.5 and the smallest number larger than 2.5 that can be represented as a VSF? In order to do this, we have to convert 2.5 again into a VSF representation. Maybe not all the way, though. So 2.5, if we normalize it so that there's only a 1 to the left of the decimal point, then we can just divide by 2 and remultiply by 2. So 2.5 is equivalent to 1.25 times 2 to the 1. And then that means that our exponent representation will be 1. So if we have our mantissa that has 4 bits, we would take this 1.25. The implicit one would be this implicit one. Then it'll have a place value of 2 to the 1. The leftmost bit of the actual mantissa will have a place value of 2 to the 0, which is 1. And then we'll have a place value of 2 to the 1, or sorry, 2 to the negative 1, which is a half. And then 2 to the negative 2, which is a quarter. And finally, 2 to the negative 3, which is an eighth. And if we look at this 0.25, that's a quarter. So we'll put a 1 there. So the actual representation of this number would be here. Then if we take this last bit and change it from a 0 to a 1, we have made the smallest increment that we can possibly make in order to get to the next number. And so what is the place value? Well, it's 2 to the negative 3, which is 1/8, or in decimal, that is 0.125. So our gap is 0.125. And that is all of problem 4. Moving on to problem 5, we have our latches and flip-flops. We're supposed to complete the timing diagram, one for a D-latch and the other for the rising edge triggered D flip-flop. It says if it's unknown, use a bunch of slashes to show that it's unknown. Assume there's no meaningful delay, meaning the delay exists, but it's so small we can't really see it on this graph. And it says in the case of the latch, C is the gate input. In the case of the flip-flop, C stands for clock, D will stand for data for both. And so let's see, data and clock. So we have to remember how the latch and flip-flop operate. So when we have the latch, so while our gate, which is C, is a 1, it's high, we copy the input signal to the output. So we copy the input signal to the output. When we have a flip-flop, we will copy the input value, using that word value, not signal. We'll copy the input value to the output at the precise moment when the clock goes from 0 to 1. And so in the clock, we'll be looking at this edge here, this edge here, this edge here, and this edge here. Those are really the only things that are going to matter for the flip-flop. When we're looking at the latch, we're looking at the entire range of time when the clock is high. That's this range, this range, this range, this range, and this range. That's what's going to matter to us in this problem. And then otherwise, both of them are the same, and they'll just keep their last value. So let's do the latch first. So latch starts off with the clock high. So we're just going to copy the signal, the input signal to the output. So that means that all of this right here, we just copy. So it goes low, and it goes high there, it goes low again, it goes low. And then in the time where the gate is low, I'm just going to keep the output at low, because that was the last value that we read from data. Then the clock goes high again. So for that entire range, I'm just going to copy the signal down. So it will be low, then high. And then while the gate is down, they'll just keep that high value. Then the clock has another high range, and so we'll just copy the signal again. So it stays high, then it goes down, and then it stays low. And then while the clock is low, we'll just keep that low value. So notice that this is the first point where we actually have a value that is inconsistent with the data input. So the latch output should look closer to the data waveform than the flip-flop will. And that's because this is the first instant, this change in data is the first instant where we had a data change while the clock was low. So it won't be reflected in the latch at this point until the clock goes high again. So when the clock does go high again, we see, all right, now our signal is high, and then it'll go low. And so we're just going to copy that again. So at this precise moment, it'll go up, stay up for a little bit, then go down, and go across. When the clock is low, once again, we will retain that low value. Then the clock is high again, so we just copy that final range of signal. It goes, stays low for a while, goes high, goes low again, and then it'll finish out. So now we've been through all that. So now we're going back to our edges in order to do our flip-flop. So we only have to look at the edges, otherwise retain a value. So when we start off, we haven't had a high clock edge yet. So that means the flip-flop will have whatever value from the last clock edge. We don't see the last clock edge, so we have no way of knowing what that value is. And so we should start off until the first clock edge with an unknown value in our flip-flop. But as soon as we get that clock edge, we see what the data value is. It's a 0. And so it'll be a 0 until the next clock edge. And then we have a clock edge. We see what the value is. It's a 1. So we're going to flip our output to a 1 and retain that until the next clock edge. At that clock edge, it's still a 1. So we can keep it at a 1 for that entire cycle. Then we have another edge where the data input is a 0. So we'll flip it down to a 0, and it'll stay like that. So this is our final answer. You can see it more clearly with the solution here. Yeah, so the latch, we can see really clearly, only differs from the actual data in kind of this range here. But the flip-flop is just really completely separate from the data, except at those clock edges. That's where they match up. All right, let's move on to problem 6. Problem 6, sorry about that, had a little formatting issue. These are line numbers, but only for, or I guess the object file. Really, if we annotate the addresses or the PCs of the assembly code, we would have PC 0 here, and 1, and 2, and 3, 4. I'll go ahead and fill out 5, 6, 7, 8, 9. And so the instructions on the same line as the output in the object file should correspond. So we are given the task to take this LC2K assembly code file and turn it into an object file the exact same way that we did for project 2A. With one exception, we are going to be putting two numbers into hex because it's easier for us to calculate. We don't need a calculator in order to do the hex. And so that'll be the only difference. So first, we'll start off with our header. Remember that the four sections for the header is instructions, or text, then data, then our symbol table, then our relocation table. And the header just tells us how many lines are in each of those sections. So we can see from the assembly code pretty clearly that we have four instructions. We can just verify that there are 6 different dot fills. That's why there's a 6 there. Then we can look at our output to kind of see how many symbol table entries we have. All these will be symbol table entries. Since this one is definitely a symbol table entry, and this one is definitely not data, we can count everything in between as a symbol table entry. So that should be 5. And then just to verify, we have 3 relocation table entries at the very end. All right. Our next blank is to translate the LW instruction into hex. And so we have to remember the bit fields for our different instructions. And I always go right to left. So remember from project 1A even that our offset field will always be 16 bits. 16 bits is equivalent to 4 hex digits. So 16 bits, 4 hex digits, and that will be our offset. Then we'll have 3 bits of register B. Then we'll have 3 bits of register A, then 3 bits of the opcode. And so that means that our hex digits will kind of overlap. So there will be like a hex digit here. So 1 hex digit will take all of register B, the last bit of register A. Then we'll have another hex digit, which takes 2 bits, each from the opcode and register A. And then our last hex digit will just copy the leftmost bit of our opcode. Okay, so if we translate this LW instruction, we'll get the op, the reg A and the reg B, and then the offset. So our LW has an opcode of 2 or 0, 1, 0 in binary. Our register A is 0, so these bits will all be zeros. Then our register B is a 3, which is 0, 1, 1. And so we can kind of see where our hex digits are going to be. And so we can ignore the leading 0 and go ahead and translate these hex digits. 1, 0, 0, 0 is an 8. 0, 0, 1, 1 is a 3. And then we can move on to the offset. In order to do the offset, this is a label. We see that the label Bob is defined. And so when we're calculating the offset, we just take the address that it's at. And we can see that it's on line 9. So we can fill in the last 4 hex digits with the representation for 9, which is really convenient because we don't really have to do any conversion since 9 itself is a hex digit. So we just put 9. So our final answer should be in hex 830009. Cool. All the rest of the machine code is done for us until we get to this line here where we're translating this dot fill of ink. Now, if we look at our assembly code file, ink, it is a label, but it's not defined. So if remember from project 2A, whenever we have an undefined label, we're just going to put a 0 there, which is really, really simple and easy. All right, now let's get down to our symbol table. And in order to do our symbol table, I'm just going to circle all of the global labels that I see in the file. So I'm going to ignore duplicates. So starting from this column here, I'm going to circle every label with a capital letter that I see. So done, R, size, and Bob. And then scanning the right side for things I haven't seen already. I've seen Bob before, I've seen R before, but I haven't seen ink. So that means that we need to see each of these 5 global labels in our symbol table. Let's see, we see the ones in the data section already defined for us, so we can kind of ignore these. We see there's one in the text section, so that means that this here has to be done because ink isn't defined in the text section. Done is defined on line 3 of the text section, so that'll be a 3. And then that just leaves ink. Ink isn't defined in the file anywhere in the text or data, so we're going to put a U there. And then for all undefined symbols in project 2A, we made the address as 0. Right, and that follows the same idea as why we put in a 0 for the machine code in the first place. So that should be easy for us. Then we have our 3 data-defined global labels, Bob, array, and size. So these offsets, we kind of get this hint from the 0 here, are section relative offsets. So we're not just copying the line anymore, the address. We're going to 0 index from the section of dot fills. So array is going to have 0, address 0 offset from the start of the data section. And we would have 1, 2, 3, 4, and 5. So Bob is on data section element number 5. And size is at data section element number 4. And so that's why we will have a 5 and a 4 for these. All right. Let's see. Now to our relocation table. We're just going to scan the right side again over here for any time we see any label being used. So that's Bob, array, and ink. Those should all appear in our relocation table. So we already see the one for Bob. Then we have array. It's on line 1 of the text section, and it is an LW that's using it. And finally, we have ink. So ink will go here. It's being used by a dot fill. And once again, this number here should be section relative for the instruction, not for the label. So the dot fill is once again on the 5th element of our data section. So we'll have a 5 here. So that is our final answer for this problem.